All right, we're going to do this. We're going to read Chapter 1 of Linux Device Drivers, 3rd edition. And notice that on this Oreilly book, they have a horse without a man. In the Running Linux 5th edition, well, I'm sure it's the same for all the editions. Oh, and I like this one, especially if there's any Western fans out there like me. Firewalls, NAT, and Accounting, Linux IP Tables, Pocket Reference, Gregor and Purdy. Come on, that's even a Western name. So let's get to reading, and it's got to be the blinding white light in the background. Sorry. This was written in 2005. Chapter 1, an introduction to device drivers. One of the many advantages of free operating systems, as typified by Linux, is that their internals are open for all to view. The operating system, once a dark and mysterious area, whose code was restricted to a small number of programmers, can now be readily examined, understood, and modified by anybody with the requisite skills. Linux has helped to democratize operating systems. The Linux kernel remains a large and complex body of code, however, and would-be kernel hackers need an entry point where they can approach the code without being overwhelmed by complexity. Often, device drivers provide that gateway. Device drivers take on a special role in the Linux kernel. They are distinct, black boxes that make a particular piece of hardware respond to a well-defined internal programming interface. They hide completely the details of how the device works. User activities are performed by means of a set of standardized calls that are independent of the specific driver. Mapping those calls to device-specific operations that act on real hardware is then the role of the device driver. This programming interface is such that drivers can be built separately from the rest of the kernel and plugged in at runtime when needed. This modularity makes Linux drivers easy to write, to the point that there are now hundreds of them available. There are a number of reasons to be interested in the writing of Linux device drivers. The rate at which new hardware becomes available and obsolete alone guarantees that driver writers will be busy for the foreseeable future. Individuals may need to know about drivers in order to gain access to a particular device that is of interest. I'm going to skip some of the non-technical stuff here. As it says here, this chapter doesn't actually get into writing code. Okay, but at least here we'll get into some technical terms that are important. So the role of the device driver. As a programmer, you're able to make your own choices about your driver and choose an acceptable trade-off between the programming time required and the flexibility of the result. Though it may appear strange to say that a driver is flexible, we like this word because it emphasizes that the role of a device driver is providing mechanism, not policy. The distinction between mechanism and policy is one of the best ideas behind the Unix design. Most programming problems can indeed be split into two parts. What capabilities are to be provided, that is the mechanism, and how those capabilities can be used, the policy. If the two issues are addressed by different parts of the program, or even by different programs altogether, the software package is much easier to develop and to adapt to particular needs. For example, Unix management of the graphic display is split between the X server, which knows the hardware and offers a unified interface to user programs, and the window and session managers, which implement a particular policy without knowing anything about the hardware. People can use the same window manager on different hardware, and different users can run different configurations on the same workstation. Even completely different desktops, such as KDE and GNOME, can coexist on the same system. Another example is the layered structure of TCP/IP networking. The operating system offers the socket abstraction, which implements no policy regarding the data to be transferred, while different servers are in charge of the services and their associated policies. Moreover, a server like FTPD provides the file transfer mechanism, while users can use whatever client they prefer. Both command line and graphic clients exist, and anyone can write a new user interface to transfer files. Where drivers are concerned, the same separation of mechanism and policy applies. I love this example. The floppy driver is policy-free. Its role is only to show the diskette as a continuous array of data blocks. Higher levels of the system provide policies such as who may access the floppy drive, whether the drive is accessed directly or via a file system, and whether users may mount file systems on the drive. Since different environments usually need to use hardware in different ways, it's important to be as policy-free as possible. When writing drivers, a programmer should pay particular attention to this fundamental concept. Write kernel code to access the hardware, but don't force particular policies on the user. Since different users have different needs, the drivers should deal with making the hardware available, leaving all the issues about how to use the hardware to the applications. A driver then is flexible if it offers access to the hardware capabilities without adding constraints. Sometimes, however, some policy decisions must be made. For example, a digital I/O driver may only offer byte-wide access to the hardware in order to avoid the extra code needed to handle individual bits. You can also look at your driver from a different perspective. It is a software layer that lies between the applications and the actual device. This privileged role of the driver allows the driver programmer to choose exactly how the device should appear. Different drivers can offer different capabilities, even for the same device. The actual driver design should be a balance between many different considerations. For instance, a single device may be used concurrently by different programs, and the driver programmer has complete freedom to determine how to handle concurrency. You should implement memory mapping on the device independently of its hardware capabilities. Or you could provide a user library to help application programmers implement new policies on top of the available primitives and so forth. One major consideration is the trade-off between the desire to present the user with as many options as possible and the time you have to write the driver, as well as the need to keep things simple so that errors don't creep in. Policy-free drivers have a number of typical characteristics. These include support for both synchronous and asynchronous operation, the ability to be opened multiple times, the ability to exploit the full capabilities of the hardware, and the lack of software layers to simplify things or provide policy-related operations. Drivers of this sort not only work better for their end users, but also turn out to be easier to write and maintain as well. Being policy-free is actually a common target for software designers. Many device drivers indeed are released together with user programs to help with configuration and access to the targeted device. These programs can range from simple utilities to complete graphical applications. Examples include the Tune LP program, which adjusts how the parallel port printer driver operates, and the graphical Card CTL utility that is part of the PCMCIA driver package. Often a client library is provided as well, which provides capabilities that do not need to be implemented as part of the driver itself. The scope of this book is the kernel, so we try not to deal with policy issues or with application programs or support libraries. Sometimes we talk about different policies and how to support them, but we won't go into much detail about the programs using the device or the policies they enforce. You should understand, however, that user programs are an integral part of a software package, that even policy-free packages are distributed with configuration files that apply a default behavior to the underlying mechanisms. And to be clear about who we is, when I read that in the book, I'm talking about Jonathan Corbett, Alexandro Rubini, and Greg Croa Hartman. Okay, so splitting the kernel. In a Unix system, several concurrent processes attend to different tasks. Each process asks for system resources, be it computing power, memory, network connectivity, or some other resource. And the kernel is the big chunk of executable code in charge of handling all such requests. Although the distinction between the different kernel tasks isn't always marked, the kernel's role can be split. So the first role is process management. The kernel is in charge of creating and destroying processes and handling their connection to the world outside. Input-output. Communication among different processes through signals, pipes, or interprocess communication primitives is basic to the overall system functionality and is handled by the kernel. In addition, the scheduler, which controls how processes share the CPU, is part of a process management. More generally, the kernel's process management activity implements the abstraction of several processes on top of a single CPU or a few of them. Next is memory management. The computer's memory is a major resource, and the policy used to deal with it is a critical one for system performance. The kernel builds up a virtual addressing space for any and all processes on top of the limited available resources, and the different parts of the kernel interact with the memory management subsystem through a set of function calls, ranging from the simple malloc-free pair to much more complex functionalities. Then we have file systems. Unix is heavily based on the file system concept. Almost everything in Unix can be treated as a file. The kernel builds a structured file system on top of an unstructured hardware, and the resulting file abstraction is heavily used throughout the whole system. In addition, Linux supports multiple file system types, that is, different ways of organizing data on the physical medium. For example, disks may be formatted with the Linux standard ext3. I almost said 4 just because it is the year 2024 when I'm reading this. And there are other examples of commonly used FAT file system, or several others. Okay, 2 more. A device control is another role. Almost every system operation eventually maps to a physical device. With the exception of the processor, memory, and a very few other entities, any and all device control operations are performed by code that is specific to the device being addressed. That code is called a device driver. The kernel must have embedded in it a device driver for every peripheral present on a system, from the hard drive to the keyboard. And the tape drive, nice example. This aspect of the kernel's functions is our primary interest in this book. Alright, I hope we go really in on tape drives. Let's read about that. The last role is networking, must be managed by the operating system because most network operations are not specific to a process. Incoming packets are asynchronous events. The packets must be collected and identified and dispatched before a process takes care of them. The system is in charge of delivering data packets across program and network interfaces, and it must control the execution of programs according to their network activity. Additionally, all the routing and address resolution issues are implemented within the kernel. All the routing and address resolution. Interesting. This is implemented within the kernel. Now, loadable modules. One of the good features of Linux is the ability to extend at runtime the set of features offered by the kernel. This means that you can add functionality to the kernel and remove functionality as well, while the system is up and running. Each piece of code that can be added to the kernel at runtime is called a module, and the Linux kernel offers support for quite a few different types or classes of modules, including but not limited to device drivers. Each module is made up of object code, not linked into a complete executable, that can be dynamically linked to the running kernel by the ensmod program and can be unlinked by the rm remove mod program. Okay, so this is probably insert. Figure 1 identifies different classes of modules in charge of specific tasks, and a module is said to belong to a specific class according to the functionality it offers. The placement of modules in Figure 1.1 covers the most important classes, but is far from complete because more and more functionality in Linux is being modularized. So let's jump down there. This is a split view of the kernel, it says. The gray box says features implemented as modules. And they're littered all over the place there. So at the top, system call interface. Yes, this is what I care most about, system calls. So these can go to any of these or these down here. The arrows are not a direct one-to-one or something. They probably should have done just one arrow to the dotted box. Anyways, we have file system type modules, and then block device modules, character device modules, IF. Oh, is that input file drivers? Well, all of this can go out to hardware. Maybe we will find out what IF means really soon. Let's continue reading. The section is called Classes of Devices and Modules. The Linux way of looking at devices distinguishes between 3 fundamental device types. Each module usually implements one of these types, and thus is classifiable as a character module, a block module, or a network module. This division of modules into different types or classes is not a rigid one. The programmer can choose to build huge modules implementing different drivers in a single chunk of code. Good programmers nonetheless usually create a different module for each new functionality they implement, because decomposition is a key element of scalability and extendability. I like how they put that there. Basically, you have the freedom to do what you want, but of course with freedom comes consequences for bad choices. Okay, so character devices. This is one that can be accessed as a stream of bytes, like a file. And a character device is in charge of implementing this behavior. So a driver usually implements at least the open, close, read, and write system calls. Okay, so this device driver implements these system calls. The text console /dev/console and the serial ports /dev/tty s0 and friends, right? So S1, S2, S3, whatever. These are examples of character devices, as they are well represented by the stream abstraction. Character devices are accessed by means of file system nodes, such as device TTY1 and device LP0. The only relevant difference between a character device and a regular file is that you can always move back and forth in the regular file, whereas most character devices are just data channels, which you can only access sequentially. There exist, nonetheless, character devices that look like data areas, and you can move back and forth in them. For instance, this usually applies to frame grabbers, where the applications can access the whole acquired image using mmap or lseek. And we have block devices. Like character devices, block devices are accessed by file system nodes in the /dev directory. And a block device is a device, for example a disk, that can host a file system. Okay, keyword I think there, host. Maybe think block party, you would have a host of such a party, host of a party. In most Unix systems, a block device can only handle I/O operations that transfer one or more whole blocks, which are usually 512 bytes, or a larger power of 2 bytes in length. Linux instead allows the application to read and write a block device like a character device. It permits the transfer of any number of bytes at a time. As a result, block and character devices differ only in the way data is managed internally by the kernel, and thus in the kernel driver software interface. Like a character device, each block device is accessed through a file system node, and the difference between them is transparent to the user. Block drivers have a completely different interface to the kernel than character drivers. So they leave us on a cliffhanger there, and they don't give us any more details or examples of that completely different interface. Well, our last one here is network interfaces. Any network transaction is made through an interface, and that is a device that is able to exchange data with the other hosts. Usually an interface is a hardware device, but it might also be a pure software device, like the loopback interface. A network interface is in charge of sending and receiving data packets, driven by the network subsystem of the kernel. Without knowing how individual transactions map to the actual packets being transmitted, many network connections, especially those using TCP, are stream-oriented, but network devices are usually designed around the transmission and receipt of packets. A network driver knows nothing about individual connections. It only handles packets. Not being stream-oriented device, a network interface isn't easily mapped to a node in the file system, as dev TTY1 is. So the Unix way to provide access to interfaces is still by assigning a unique name to them, such as eth0. But that name doesn't have a corresponding entry in the file system. Communication between the kernel and the network device driver is completely different from that used with car and block drivers. Instead of read and write, the kernel functions relate to packet transmission. And they don't give us the example of those sys calls. Well, there are other ways of classifying driver modules that are orthogonal to the above device Types. In general, some types of drivers work with additional layers of kernel support functions for a given type of device. So for example, one can talk of universal serial bus modules, serial modules, SCSI modules, and so on. Every USB device is driven by a USB module that works with the USB subsystem, but the device itself shows up in the system as a character device, like a USB serial port, say. A block device, like a USB memory card reader, or a network device, a USB Ethernet interface, Other classes of device drivers have been added to the kernel in recent times, including FireWire drivers and I2.0 drivers. In the same way that they handled USB and SCSI drivers, kernel developers collected class-wide features and exported them to driver implementers to avoid duplicating work and bugs, thus simplifying and strengthening the process of writing such drivers. In addition to device drivers, other functionalities, both hardware and software, are modularized in the kernel. One common example is file systems. A file system type determines how information is organized on a block device. In order to represent a tree or directories and files, such an entity is not a device driver, in that there's no explicit device associated with the way the information is laid down. The file system type is instead a software driver because it maps the low-level data structures to high-level data structures. So the file system type is a software driver. It is the file system that determines how long a file name can be and what information about each file is stored in a directory entry. The file system module must implement the lowest level of the system calls that access directories and files by mapping file names and paths, as well as other information such as access modes, to data structures stored in data blocks. Such an interface is completely independent of the actual data transfer to and from the disk, or other medium, which is accomplished by a block device driver. So if you think of how strongly a Unix system depends on the underlying file system, you'll realize that such a software concept is vital to system operation. The ability to decode file system information stays at the lowest level of the kernel hierarchy and is of utmost importance. Even if you write a block driver for your new CD-ROM, it is useless if you are not able to run ls or cp on the data it hosts. Linux supports the concept of a file system module whose software interface declares the different operations that can be performed on a file system inode, directory, file, and superblock. It's quite unusual for a programmer to actually need to write a file system module because the official kernel already includes code for the most important file system types. And I remember watching a video on a Linux conference where somebody said there are like 50 different file system types out there. And then the C programmers argued with the Rust implementers. Okay, security issues. And because this book is so old, 2005, I bet you we are missing a lot of important information. But let's see what they say here. Security is an increasing important concern. In modern times, we'll discuss security-related issues as they come up throughout the book. There are a few general concepts, however, that are worth mentioning now. Any security check in the system itself is enforced by kernel code. If the kernel has security holes, then the system as a whole has holes. In the official kernel distribution, only an authorized user can load modules. The system call init_module checks if the invoking process is authorized to load a module into the kernel. Thus, when running an official kernel, only the super user, or an intruder, who has succeeded in becoming privileged, can exploit the power of privileged code. So when possible, driver writers should avoid encoding security policy in their code. Security is a policy issue that is often best handled at higher levels within the kernel, under the control of the system administrator. There are always exceptions. However, as a device driver writer, you should be aware of situations in which some types of device access could adversely affect the system as a whole and should provide adequate controls. For example, device operations that affect global resources, such as setting an interrupt line, which could damage the hardware loading firmware for example, or that could affect other users, such as setting a default block size on a tape drive, are usually only available to sufficiently privileged users, and this check must be made in the driver itself. Device writers must also be careful, of course, to avoid introducing security bugs. The C programming language makes it easy to make several types of errors. Speaking of the C versus Rust debate, many current security problems are created, for example, by buffer overrun errors, in which the programmer forgets to check how much data is written to a buffer, and data ends upwritten beyond the end of the buffer, and thus overriding unrelated data. Such errors can compromise the entire system and must be avoided. Fortunately, avoiding these errors is usually relatively easy in the device driver context, in which the interface to the user is narrowly defined and highly controlled. Some other general security ideas are worth keeping in mind. Any input received from user processes should be treated with great suspicion. Never trust it unless you can verify it. Be careful with uninitiated memory. Any memory obtained from the kernel should be zeroed or otherwise initialized before being made available to a user, process, or device. Otherwise, information leakage, such as disclosure of data, passwords, etc., could result. If your device interprets data sent to it, be sure the user cannot send anything that could compromise the system. Finally, think about the possible effect of device operations. If there are specific operations, for example, reloading the firmware on an adapter board or formatting a disk, that could affect the system, those operations should almost certainly be restricted to privileged users. Be careful, also, when receiving software from third parties, especially when the kernel is concerned, because everybody has access to the source code, everybody can break and recompile things. Although you can usually trust pre-compiled kernels found in your distribution, you should avoid running kernels compiled by an untrusted friend. If you wouldn't run a pre-compiled binary as root, then you'd better not run a pre-compiled kernel. For example, a maliciously modified kernel could allow anyone to load a module, thus opening an unexpected backdoor via init module. Note that the Linux kernel can be compiled to have no module support whatsoever, thus closing any module-related security holes. In this case, of course, all needed drivers must be built directly into the kernel itself, and it is possible with 2.2 and later kernels to disable the loading of kernel modules after system boot via the capability mechanism. Okay, so I think you guys would forgive me for skipping this section on version numbering. Is this how they're going to end chapter 1? Okay, they'll go into licensing terms, something also very skippable for me. Okay, yes, the kernel mailing list can have quite a few messages per day. And then overview of the book we will also skip. So thanks for reading along with me. And I'll start chapter 2 in the next one.